Now let's see about the diffraction grating. What is meant by diffraction grating? The diffraction grating is an optical element that divides the light composed of lots of different wavelengths, example white light, into a light component or component by wavelengths. This is referred to as diffraction grating. The simplest type of grating is one with a large number of evenly spaced parallel slits. An arrangement consisting of a large number of equidistant parallel narrow slits of equal width separated by equal opaque portions is known as diffraction grating. The plane transmission grating is a plain sheet of transparent materials on which opal rulings are made with a fine diamond pointers. The modern commercial form of grating contains about 6,000 lines per centimeter. You are able to see the parallel narrow slits of equidistant. The rulings act as obstacles having a definite width B and the transparent space between the rulings act as a slit of width A. The combined width of a ruling and a slit is called as grating element. The point on successive slits separated by an equal distance equal to the grating element are called corresponding points. MN represents the section of a plane transmission grating. Over here, AB, CD and EF are the successive slits of equal width A and BC and DE with the rulings of equal width B. So let E is equal to, the grating element is equal to A plus B. Let a plane wavefront of monochromatic light of wavelength lambda be incident normally on the grating. According to Huygens principle, the points in the slit AB, CD, etc. as a source of secondary wavelets which spread in all directions on the other side of the grating. Let us consider the secondary diffracted wavelets which makes an angle theta. The path difference between the wavelets from one pair of corresponding points A and C is given by CG equal to A plus B into sin theta. It will be seen that the path difference between waves from any pair of corresponding points is also A plus B into sin theta. The point P1 will be bright when A plus B into sin theta is equal to m lambda, where m is equal to 0, 1, 2, 3 is an integer. In the diffracted position, theta is 0 and hence sin theta is equal to 0. So the A plus B sin theta is equal to 0 satisfies for the condition brightness for m equal to 0. Hence the wavelets proceeding in the direction of the incident rays will produce maximum intensity at the point O of the screen, and this is called as a zero order maximum or central maximum element. Moving further, A plus B sin theta 1 is equal to lambda, the diffracted wavelets inclined at an angle of theta 1 to the incident radiation or direction reinforced and the first order maximum is obtained. Similarly, for second order maximum is given by A plus B sin theta 2 is equal to 2 lambda. This is considered as a first order and this is considered as second order. On either side of the central maxima, different orders of secondary maxima formed at point P1 and P2. In general, A plus B into sin theta is equal to m lambda is the in condition for maximum intensity. Where m is an integer, the order of maximum intensity is given by sin theta is equal to m lambda divided by A plus B. So sin theta is equal to n into m lambda, where n is equal to 1 by A plus B, which gives the number of grating. So this is the equation you have seen. When white light is used, the diffraction pattern consists of a white central maximum. On both sides, continuous colored images are formed. In the diffracted position, theta is equal to 0 and hence sin theta is equal to 0. Therefore, sin theta is equal to nm lambda is satisfied for m equal to 0 for all values of lambda. Hence, at O, all the wavelengths reinforce each other, producing a maximum intensity for all wavelengths. Hence, an undispersed white image is obtained. As theta increases, the A plus B into sin theta first passes through lambda by 2 values for all colors from violet to red, and hence there will be a darkness. As theta further increases, A plus B sin theta passes through lambda values of all colors, resulting in the formation of bright images from violet to red. These spectra are formed on either side of white, the central maximum.